first thank the organizing committee for the invitation. I'm very impressed by the whole event and the campus. Today I'm going to talk about some ventures. I started this venture 3 years ago. It's a brand new topic to me. So I'm going to share our adventures, our findings, understandings. Unlike many of the presentation about these things, I also would like to share with you about the frustration, the painful things we experienced, and something interesting, I say. Definitely, we have much more understanding on this topic than 3 years ago. Okay, so this is a joint work with my collaborator, my former postdoc. These are two my former postdocs, and Haoming Zhou at the Georgia Tech. Okay, so let's start about neural network. As an object, mathematical object, or whatever you call it, it's just a form of representation. Not the traditional one we're used to, but that's it. It's a way of representing functions and mappings. So remember in my topic, I have scientific. The scientific, one thing is saying I'm mainly, from my background, I'm interested in potential use of neural network as a representation to approximate functions, mappings, operators. In particular, functions, for example, let's start with simpler things, functions. In my mind, functions are most often physical quantities, physical fields, which are best parameterized by XYZ. So which means XYZ, these coordinates, their units make sense. Not like in some other applications where you use blood pressure, your salary, your age, your weight, all these things to characterize a person. In those coordinates, it has not physical units, it has not corresponding scalings, so it's just a random embedding in some Rn. But here, I'm talking about a function which is well-defined, like temperature in this room, by XYZ. Why is that important? First of all, what are the challenges and difficulties in approximating such a function? First of all, our functions need to be approximated at all points, every point. So every point in this room, you need a good approximation. The second thing is, the quantity can take any real numbers, very different real numbers, but all possible. Not like classification. You only have class of cat, dogs, it's just a few, maybe 10 or 12. That's already pretty large classification problems. So we are also not interested in just approximating the mean, the variance, some quantities. We really want to approximate the function at every point, with all possible value well. So that's a pretty challenging task. But what is our friend? Is that usually the physical quantities have special spatial regularities. It's not totally random, very wild. It's more or less, if the temperature here is 10 degrees, it's probably nearby, it's also 10 degrees or nearby. So there's some spatial regularity we can take advantage of. When we're talking about that, another useful characterization or description of function is through Fourier domain. So basically, physical domain, Fourier domain is like a complementary dual ways to characterize a function. So in my analysis later, I'm always trying to use, often using Fourier series or Fourier domain to characterize the problem, where the difficulty is, and so on and so forth. The other scientific is, I really hope people are really talking about scientific discoveries, understandings, rather than promoting some hypes, or in some sense, you're just trying to start with the assumption you want to show it's good, it's working, then you do cherry picking of examples to show it's working. So I think it's good to know its weakness and strengths so that people know where this could be of potential advantage, where you shouldn't use it, or where the difficulty is, that you can try to improve it. So I think it's not just use it to show it works, but also sometimes I think a lot of the comparison, people do not compare the results with the state of the art using other methods. It's just compare with other network representations. I think that's also not the right way to do comparison. Comparison compare with all other methods. So try to show whether it's good or bad, all those things. Okay, so let me start with the main talk of this presentation. So if you look at it as a representation, first of all, it's a nonlinear representation and parametrized, nonlinear parametrized. You have so many parameters, and it's nonlinear. So nonlinear, which means, first let me tell you what is a linear representation. So usually when we do scientific computing, or we usually approximate an arbitrary function, what do we do? Most likely, we use some building blocks, Legos we're familiar with, like polynomials, sine, cosine, finite element basis. You use those building blocks, and you try to use linear combination of them. So your recipe is just what are the linear combination coefficients. But the building blocks do not depend on your function. So that's linear. So in a sense, I give you a Fourier series. I don't care what function. I use sine x, sine 2x, sine 3x, da, da, da. Okay, it's independent, the function I'm going to try to approximate. But if you talk about nonlinear, there are a few nonlinear methods. For example, if you understand, Gaussian mixer model or using radial basis function, the bases are Gaussians, but their center, the variance, depends on the function. You try to optimize this to, you not only just the fixed Gaussians, but you use variable Gaussians to do that. So it's nonlinear. There's other nonlinear things, but that's usually things. So the nonlinear means it's the representation depends on the function you try to approximate. Okay, so if you look at what are the important ingredients in this neural network representation, one is network structure. Most of the time, people just usually fully connected. And the activation function, people use ReLU, use sigmoid, use different activation function. And many times, because it's a nonlinear representation, inertialization is very important, because if you do one versus the other, because it's nonlinear, you could very easily get tracked to local minimum. So using difference initialization can also help you. This is, I don't think it has been too much investigated. So those are the three things you can control, you can design, and hopefully you're trying to design them. I haven't talked about the next important ingredient is optimization. Hopefully this is combined well, fits well, to work well together with optimization. Learning, well, we use fancy word learning, but it's just optimization. Well, the pros of this network, many people find, especially engineers, they don't want to do a mesh, do the finite element method. Well, it's very flexible and very simple and works sometimes like charm, but sometimes it's very frustrating because it's like a black box. Well, many people like black box, but I think black box is a cons, because I don't believe black box works for everything. If you have a very difficult problem, you shouldn't trust a black box. You should have some understanding what is working and put structures, information, prior knowledge into the method rather than just using a black box. If we all know nowadays a big business in this is you have to do parameter tuning. Usually professors do not do this. The students have to do a lot of parameter tuning. For example, the width, the depth, so on and so forth. And most of the time, the optimization is quite expensive computationally, time consuming. You have to run 1,000, 10,000 epochs. And the worst is if something goes well, you're happy. But if something does not go well, you're very frustrated because you don't know what it means, you know. You don't know what, you don't have the understanding what it's doing, so it's very difficult to improve it. Parameter tuning, there's billions of parameters. How do you tune those, right? So to me, a lot of questions needs to be answered. And I think mathematics plays a key role in this task. Okay, so if you're talking about why do I use a nonlinear representation, I think the ultimate goal is the potential, whether you can achieve it or not, that's a different story, but the hope is you want to approximate a very complicated function or task, but you only do it once, so you want it to adaptive. You don't want to use the basis someone give to you, which does not fit your target well, so you may need to, the problem with use linear method is you have to provide enough basis, enough Legos in order to put them together to do approximate a complicated task. So in that sense, that's the disadvantage of that. So you have to provide it. That's usually what we call curse of dimension. Usually you don't want to do computation more than 3D. Okay, that's already very difficult nowadays. It's adaptivity. But I guess the most important theorem in life is no free lunch theorem. So in a sense, you have to pay, you have to learn, you have to optimize. That's the things to achieve the adaptivity, okay? And most of the time, the optimization become the bottleneck, okay? To achieve this potential. It's not easy because it's non-convex, non-linear, all the things here. Especially nowadays, we're talking about large-scale problems. You know, it's tens of billions, even more than hundreds of billions of parameters. So with that many large-scale problems, the only possible way to do is optimization is through gradient descent based method, because it's very difficult to compute the form the Hessian. You can only mainly compute the gradient. And you based on that, you have different version, but it's basic gradient descent-based method. If you talk about gradient descent-based method, what is the most challenge to such gradient-based method? Okay, so well, your first thing you say, it's a local one, because when you go down the hill, you only locally, and you know that's where the gradient direction, you do something around that direction, so that's all you can do. It's very local, so first of all, it's very difficult to find there's another valley down there. If you are nearby, there's a valley, so that's local. But to me, that's still the secondary in most practice. The thing is sensitive to air conditioning. So which means if you have billions of direction you want to minimize, all direction you can minimize, some are very sensitive, some are very insensitive. So in some sense, if mathematically speaking, if you can compute the Hessian as a matrix, that matrix is very ill-conditioned. Mathematically, there are only two types of matrices, invertible, non-invertible. But for numerical computation, matrices are very, very different. And conditioning. So in general, if you're talking about a matrix, you look at SVD. Okay, this is the index of the singular values, and this is So I mean the very spectral, very fast decay, okay? So if you have something, mathematical definition is a little bit different. If you have a matrix, singular value O equal to 1, and suddenly becomes 0 or very small, that's also called ill-conditioned, because this ratio is very big, but you just remove one dimension, everything is well conditioned. So what I mean is you have a continuous spectrum, like continuous spectrum, and it decays very fast. Okay. So that's ill conditioning. And all those directions or eigencomponents corresponding to the singular values are very difficult to capture, to learn. Okay, so that's conditioning. It's caused trouble to get good accuracy, stability, and efficiency. Okay. Even, for example, you do this, when you solve ax equal to b, right? You can look at, by minimizing this one, it's a quadratic function, only one local minimum, which is global minimum, quadratic. If A is a 1,000 by 1,000 matrix, 1,000 by 1,000 matrix, if it has ill conditioning, you do gradient descent-based method, you're already doomed. Okay, so you're already doomed. There's no local versus global yet. There's only one global minimum, but the conditioning. So another thing I'm trying to say is numerical analysis, classical things, classical wisdom still valid for all the new things. So if you just do this as a black box, you only need 1 semester of multivariable calculus, 1 semester of linear algebra. You can do this, but to understand how well, I think all those mathematical analysis series still play a very important role. So you will see. So here, there's a special situation. Many people start with a good approximation things like Kolmogorov, Arnold, decomposition. It's very beautiful mathematically, but it's very, very unfriendly to this type of optimization method. It's almost impossible to do that. So I think now there is time to think the other way around. If I only can do gradient-based descent method, can I design a structure, activation function, initialization so that it's friendly to gradient-based method? Okay, so I think the other way around may be more fruitful rather than I have one and you just, because gradient descent-based method is very, very primitive. It's not a fancy good way to deal with even, especially the ill conditioning things. So another thing is, I think from my own experiences, is that computation meaningful, interesting, not using simple problem to test it. You can use low dimensional problem. You don't need to go to 100 dimension. I even don't know how to measure errors in 100 dimensions or sample functions, not just a simple Gaussian, but more complicated function in 100 dimensions. But many examples in 2D, 3D, you do that, you will find the phenomenon. You can study very well many things. So you don't need to go to super high dimension, which is usually we cannot afford to compute. But here, understanding, you can do that. So computation is very important. A lot of series, I will quote a few series, like universal approximation series. It's so beautiful, right? But many times, it doesn't mean practically you can do that. I will show you example later. So you need to use computation to show whether your construction, because most of your nice construction is highly constructive, highly nonlinear, highly non-convex. So you do not expect gradient-based method to find those solutions. So impossible. So using computation to justify your things is working rather than usually there's a big gap. There's a big gap. Okay, so as mathematician, the best way to do is simplify the problem, but capture the key properties or information features. So let's start with 2 layers. 2 layers is of this form, right? This is each neuron. Sigma denote the activation function. There's 3 parameters, AI, WI, BI, C, all these are parameters, okay? But it's of this form, okay? Fully connected 2-layer neural network is of this form. Okay? So activation function and 2-layer, there's no structure you can change. It's always fully connected. And no, but this, if you look, that's give you the closest link to our previous linear representation. So if you fix these parameters, WI and BI, which hopefully, potentially give you the adaptivity, but you fix these things, then this is just a linear combination of a family of bases. So to me, every neuron is like a basis. You use a linear combination of bases to approximate the function you want. Period. That's the form. We all know that's the basis. Family of bases is parameterized by this Wi and Bi. You look at that, you minimize this least square. You can do other things, but you can always find, let's stick to this simple one. And you know the exact solution. Where the G, I want to emphasize, that's the most important things I will emphasize in the first part, is the gram matrix. In finite element, we call it its mass matrix. In linear algebra, we call it normal matrix, but it's really nothing. It's just the correlation or inner product between each pair of the bases. Okay, that's called the gram matrix. And the right-hand side is just a projection of F to this basis here. Okay, if you're talking about the important mathematical questions, it's very important. I think this is the starting point for all our previous study. What is a good basis, right? The good basis means when you increase the number of bases, building blocks, the error decays very quickly. So for example, if you have a periodic and smooth function, this distance from, if F is smooth and periodic, this distance decays exponentially fast in terms of n. So that's something you like for, but usually maybe polynomial is okay, linear is just too slow. So you really want to say, okay, when I add more bases, which cause more computation costs, the error decays very fast. That's the first mathematical question you should study. We all know free basis is good for smooth periodic function, but it's not good for function not periodic with some singularities or some non-smoothness in general. So you know all what are good or not good for. So there's no one basis good for everything. So in terms of representation. Approximate, yeah. But that's not the end of the story. But when you really need to compute, find those AIs, G is the key issue. So what are the things? The spectral property, whether it has this ill conditioning, that would be bad, period. If you have a basis, give you these things, you should stop using that basis because it gives you all the trouble in accuracy, efficiency, and so on. And the sparsity of G, because if you have sparse G, you can apply G to a vector very quickly. You can find efficient iterative method. So it's all related to computation cost of G and G inverse. And the choice of basis is very important. Okay, so the next thing is, let's make things even easier. Let's make the activity function is ReLU. Okay, just in case some people do not know ReLU. ReLU is a very simple function, 0 and identity. Okay, it's just this ReLU. And you can shift, this is the bias you can shift. Here, the bias is 0. Okay, so then you know, after a little calculation, this, a bunch of this will span the same space as this finite element basis, hat function. Okay, they span the space of piecewise linear function. Okay, continuous piecewise linear function. Well, mathematically, that's it. They're the same, no difference. But numerical, the two sets of bases is very, very different in terms of computation. So for finite element basis, it's local, right? So this basis only interact with its two next neighbors, no others. So the matrix is sparse, that's something good. The more important good property is any two bases, they form an angle bounded away from zero, right? When we do vector decomposition, what basis you like most? Orthogonal basis, right? You can do one by one. You don't solve them simultaneously. Otherwise, you have to solve a linear system. And the worst scenario, when their bases are very close to parallel. Because when you decompose a vector to two such vectors, it's very sensitive and it's very difficult, okay? So, of course, freest basis is the best because they're just, everyone is orthogonal to each other. But to design this global basis and use it in high dimension is impossible because you have to do the integration. You have to have fast FFT. Then in high dimension, it's very difficult, become more and more difficult. So, well, there's a well-developed finite element theory to tell you the grand matrix for finite element basis has a condition number of order 1. Okay, order 1. So there's no ill condition at all. So which means no frequency bias. They treat all frequency the same way because the condition number is almost constant. If you don't have an adaptive mesh, you have uniform mesh, that's just, you will see that. It's just flat. So it can capture all frequencies as long as it can be resolved, the mesh size. Every frequency is equal. But when we use ReLU basis, first of all, it's global, so every basis interact with all the others. So the grand matrix is dense. Not only that, if you have two such bases, when this is small, then these two bases are highly correlated. So it's basically related to the cosine angle is equal to 1 minus this distance squared. So which means if you have more and more these things, that's where the universal approximation will break down because you're creating more and more ill-conditioned things. It doesn't help you to capture anything because it's when this is closer and closer, it's too highly correlated. So we will give a very specific estimate about how fast the spectral decays in 1D, 2D, NED. So it's ill-conditioned. And, well, you not only need the spectrum analysis, you need to know the eigenmode because you know if the spectrum looks like this mode, the eigenmode corresponding to this smaller, the bigger eigenvalue, singular values or eigenvalues, are your biased towards. And those modes corresponding to these ones, it's biased against. It's very difficult to capture. So those modes are easily captured, easily used, it's easily captured. So for this, these are the low frequency mode. For when you use ReLU or anything, any global activation function you use, eventually the leading ones corresponding to low modes, low Fourier mode, and those smaller eigenvalues, those modes are corresponding to higher frequency modes. So which means you're biased again high frequency mode, which is not too bad in practice because it means it's biased towards stability than accuracy. So, and a universal approximation theory does not tell you can do everything. Even you have more and more bases, you have more and more those things, you only increase the mode, you increase the things here. How many mode you can capture, usually this is determined by your size times your basically machine precision. Even you have a 2 double digit, whatever that's machine precision, machine is as a round off error, that's round off error. And that determines how many modes you can capture. You're adding more and more wider network, you're just adding modes into here. You're not going to capture it stably or accurately. So period. So universal approximation, I show you, doesn't mean much when you do computation. Which basis does not have universal approximation property, right? It doesn't mean Fourier has one, it's always good for everything. So you have to know what is good for, what is not good for, okay? No matter how this is. And it's basically, if you're using two-layer neural network, it's mainly a low-pass filter. It's a low-pass filter. Okay, where the spectrum come from is from studying this kernel, which is the activation function with bias at x, activation function with bias at y. You look at that, it has a kernel look like this. The xy is the bias, where the bias. So you find the correlation between the neuron or ReLU basis with bias at x and ReLU basis with bias at y. It has this form. And the singularity is very important. If you don't have these three, roughly tells you, if you take full derivative, it's a delta function, you'll get a fourth order ODE with boundary value problem, and you will see you can explicitly compute the eigenmode and eigenvalues. The eigenvalue decay like k to the minus 4, because the 4 here, because the 3 here. And although it's a combination, the eigenmode exponential function in the Fourier modes, but this exponential part decays very quickly. So after 10, it's basically you can regard it as a Fourier modes. Okay, so, and we can generalize to not evenly more randomly distributed points, the bias, but roughly this is what you can expect. Very ill condition. If you solve elliptic PDE, it's because second order PDE is only k to the minus 2. But that one for differential operator, it's biased towards high frequency, biased against, because sine 100x, you get 100 squared. If you take two derivatives, you have 100 squared times sine 100x. So differential operator biased towards high frequency. And the neural network, very interesting, is representation, 2-layer, at least here I'm related 2-layer, so it's biased towards low frequency. Okay, so we can do any dimension. The only thing you have to notice is that this function, ReLU function, again, the singularity is at a hyperplane. If you take two derivatives, it becomes a delta function supported on that hyperplane. So basically, you have the Radon transform of your second derivative of the function you want to approximate. So it's really the Radon transform. You do something, you can find out the spectrum decays like this. Okay, D is the dimension. Okay, and the eigenmode roughly is the eigenfunction for Laplace operator. And also, if you, because when you solve PDEs, you cannot use ReLU. It has no derivative. You use ReLU square, ReLU cube, So this is the spectrum decay with in D dimension when you use ReLU to the mth power. What you observe is the smoother, the lower order the singularity, the faster the decay. That's what ReLU is good when people find using that. It's because it has the best representation power among activation function. But I'll tell you later there's something else you can do that make a difference. But in general, ReLU is, in this particular case, due to its singularity, it's higher orders, it's most singular, it gives you the most slowest decay, which is the most representation power. Okay, the decay of this tell you the representation power. Okay, the fast spectral decay. So that's just numerical to show. The blue is a numerical result. The red one is perfect slope -4. It agree very well. When you do adaptively, you're not uniformly grids. Actually, you can imagine it should be worse because there are two bases with closer bias. Okay, ReLU function is even worse. So adaptive even. So that's related later. I'm going to talk about the best hope we have to have adaptivity, but adaptivity comes with the cost. And with this representation, you cannot effectively doing adaptivity. Okay, this is 2D. Okay, so from representation, ill conditioning in representation bias against the high frequency. Well, that also directly tell you when you do training, learning, you have the same bias. So this is just, you do the ODE, simply ODE, you will find for different eigenvalues, that mode, error in that mode decays this fast. So when lambda k is small, decay very slow. So basically, you need at least this much time for the case mode to converge to make a significant reduction in the error. This is the solution. This is the error at the beginning. You want to reduce to 0 related to this. And if you have small lambda k, this decay is very small. Okay? Convergence of gradient descent-based optimization depends heavily. Usually, it's the number of iterations you need with the condition number kappa. The number of iterations is proportional to kappa. So which means, if you want to compute k to 100, then that means 10,000 already. You need 10,000 iterations, just 100 more in 1D. Okay, so then you tell me I'm cheating because there's something very important I ignore so far. That is this one. Okay, for ReLU, that constant can always pull out because that's a homogeneous degree 1. So there's only one extra parameter you can play with, which is the bias. So hopefully, what you want to have, ideally, if you want to approximate a function, have a fast transition here, you definitely want to put more BI here, less bias here. So it's like a grid. For me, the bias point is like a grid. Okay, so you want to put more BI here so you can capture this fast transition. Well, that's the hope. Hopefully, by doing optimization, this is optimization of gradient descent for this, minimizing these things with respect to both AI and BI. You have this is nonlinear, non-convex. Already ODE system is very difficult to analyze. And your question is, do you have hope? Can the training process obtain optimal AI, BI adaptive? So there's no such answer because given an F, I don't think anybody knows what is the best distribution the BI should be mathematically. There's no such result. Okay, but even that, somebody knows mathematically, nobody knows whether the gradient descent can go to that. That's $1 million question. But you can answer, even it can go, it has an optimal. How much does it cost to go there? Okay, so the competition cost. But let me give you an intuition why your wishful thinking does not work. Because if you want to make BIs very non-uniformly distributed, densely here, what do you need? You need to know where it is. You need high-frequency information to tell you where the function suddenly transitions very quickly. But when you initially randomly put in BI, as I showed before, that representation has no information of high frequency or very little high frequency information. So it cannot guide you to redistribute BI to here effectively. So in principle, even intuition tells you no. And also we said, when becoming more adaptive, the condition number become even worse, even harder to make it more non-uniformly, highly densely distributed here. So in general, wishful think does not work. And we don't have a sharp bound, but we can make some statement far from sharp. For M's mode, to reduce the error by half in the M's mode, you need at least this many time step. But usually you will see something between around M to the 4th, okay, according to that power. Okay, but this proof is quite technical and difficult because it's fully nonlinear, and we do it in a fully discrete sense in a bounded domain, not go to the mean field limit and in unbounded in the whole interval, in the whole real line. Okay, I don't want to. Okay, so I tell you why using the two-layer structure, what's the potential problem, and then I will also to show you something, okay, using different activation function. For ReLU, we have everything clear. But for other activation function, as long as it's smooth, not spectral decay, is exponential. This is a log plot. This is ReLU. This is that K -4 slope. So we use sine, we use arctangent, we use ReLU, first and second derivative of arctangent. pay attention here. My initialization, I'm going to talk about initialization. I initialize my W and B in the uniform minus 1, 1. That's usually the default initialization when you use PyTorch, all those things. They will default to this, okay? And you will see the spectral decay so fast for all these smooth function, except ReLU is polynomial decay. And when you use these two approximation functions, the first row to show you ReLU is the best because spectral decay is the slowest, has the best representation power. So when you have high frequency mode in this function, which is here, it can capture some, but not very well. And all other functions, not at all good. But even this is using least square, okay? I fix all those random things, the bias, and then I just do least square. Here I use atom, so which means that's the typical machine learning way to do that. You optimize both A and B. Here I fix B, just optimize A. Here I optimize both an A and B. You see, it doesn't improve too much. So that means learning is not making it more adaptive. So here are a few conclusions from our, just using the previous, our study, just based on the spectral property, we can already see the following. ReLU is the best due to the slowest decay, spectral decay. All others has more frequency bias due to exponential spectral decay. And due to bias high frequency, learning adaptivity is difficult. Okay, so there's one thing I didn't touch yet for 2-layer. I'm still on the 2-layer. That is initialization. If you remember, my W and B are initialized in minus 1 to 1. Then what it prevents you to scale it from minus S to S? Say S equal to 10, or S equal to 0.1. So what does S can change the picture? Okay, the scaling of the initial, okay, initialization of parameters. Okay, so you can see introducing, if you scale to minus 10 to 10, you definitely introduce high frequencies. Because if you're using sine as activating function, you have sine 10x in there. Before, you only have, everything is between sine alpha x, alpha is between minus 1 and 1. Everything is wiggle very slowly, no high frequency. Here, and also if arctangent, you will have very fast transition arctangent function rather than usual arctangent function. So this introducing, and also you will see it make the correlation, because you can think of increasing this is like improve some singularity. You improve it fast transition. So it decorrelate the correlation between different activation function. And you will see there's a, for sine, exactly a flat piece and drop exponentially. Other one also has quite flat piece, okay? So immediately, except ReLU not affected by this scaling. So ReLU still would be that polynomial decay, but all the other by scaling using different S, the larger S, you have more flatter regions. So which means, in principle, this says I should use S as large as possible so that all these modes can be used in my representation. I increase my representation power. Because as I said, the leading mode, how many leading modes you have determine how well you can represent. Because that's the dimension of your approximation, okay? You can use the number of bases you can use. Okay, but, well, I'll tell you, okay, that's, the whole thing is also related to this scaling is corresponding your stretch x, f of x from minus 1 to 1 to minus s to s. So if you have a fast transition here from minus 1 to 1, when you stretch it to minus 10 to 10, this transition is very slow, becomes smooth, okay? So this is equivalent to that. Then you say, okay, I just take S as large as possible. But again, no free lunch. When you have something good, then you also, there's some limitation. Life is full of constraints. You can think, when I stretch to minus S and S, if you think my bias is like laying down the grids here, you definitely would like to have enough grids. So you are too compromised. When my network width is n, that means I can only put n grid point in this in minus s to s. So you have to compromise between how large s and the resolution. In terms of Fourier, if I have minus n to n, you'd better using the Fourier mode from minus n over 2 to n over 2, so you cover the Fourier mode from any Fourier mode less than n over 2 without gap in between. So the general philosophy is your s should be proportional. You can use 0.5n, more conservatively 0.25n, but it should be linear proportional to the network width. Okay? So when I do that, you immediately see before using tanh or arctangent using sine doesn't do well, but if I scale s to n over 2, do very good job. Okay? And when I go to s over n, is everything good? But when you go to the second derivative of arctangent, because the larger derivative is of order 2. So you can think of that give you the trouble. And if s equal to 3 over n over 2, even arctangent give you this, we call it overfitting or oscillation. So this, usually you should not be too aggressive. Half n or quarter of n should be the right choice. But definitely say scaling helps you because you provide more diversity in this basis, because I'm always thinking of each neuron is like a basis. You give more diversity in these neurons, in this basis. Okay, so here I probably will try to quickly go through, but here, as I said before, you would like to know for a neural network, what are easy functions, what are more difficult functions, or what are the most difficult functions, right? Because that tells you, okay, that also give you some guidelines. When I approximate more difficult function, I use larger network, wider, more deeper. If easy function, I can use a very small network. I don't have exactly the thing, but I can tell you, this is trying to show you the highly oscillatory function is difficult. How do I show it? I show, okay, using this kind of characterization, say, these are all the possible parameter AJ, WJ, BJ you can choose. You have a domain to choose this, very high dimensional domain to choose this. You want to see, okay, among all possible these parameters, what the measure or the percentage of those parameters can give you good approximation with an epsilon. So basically you say, whether you are searching this parameter in a lake or in an ocean, seek a needle in an ocean, in a small lake or in the ocean. It's really tell you how difficult you're going to find a good coefficient, how many coefficients can give you a good approximation. And we can characterize that by these things, this probability or this percentage of these good parameters, only take this. And this kappa depends on the function you want to approximate. Directly saying is the inner product between the function you want to approximate and all the basis activation function you use. Okay, these are the bases. This is the target. Roughly saying, if you give me a bunch of, you want to approximate this vector, and you give me is a bunch of vector almost orthogonal to this vector, it's going to be hard. Okay, it's going to be hard. So this is saying, this is the reason, essential reason for this oscillatory is difficult, is because if you integrate or any tanh function, smooth things, if you integrate against this oscillatory function, it's almost zero. Highly oscillatory function, inner product with this function, well, that's only this cause the decay, something. And if you have a smooth function, then this decays exponentially with respect to this oscillation. And that number becomes exponentially small in terms of the frequency. Okay, this is the frequency. This k goes like this. And when you put in here, this probability, this percentage, is going exponentially smaller and smaller. So this tells you, so if you don't believe me, try to approximate a oscillatory function. You look at all the tests so far, how many frequencies they can test, okay? Look at those people who have done something. You look at how roughly no more than 10 most of the time. Okay, take-home message for two-layer is using parameterized global function correlated basis can lead to ill conditioning in representation, okay? Against high frequencies, okay? So the accuracy, high frequency is difficult. Here, two-layer. The most important message is this one, training of adaptive WB is ineffective. So which means you lack adaptivity. That's all the nonlinear representation potential is for. So to me, if two-layer, there's no reason to use two-layer rather than using well-developed basis, either random basis, but random basis, you don't have very structured grand matrix. If you use finite element Fourier basis, these have very structured those grand matrix to do the things, and FFT, for example. So two-layer is not useful at all. But why do we, so people say, why don't you use local activation functions? Right? I mean, I tell you, because all the analysis, because I'm using global activation function, they have strong interaction among all of them. Why do I use? Well, use local one, you cannot go to more than 3D because you have to put all the local bases everywhere. If you miss somewhere here, something happens here, you don't know. So local basis is like usually we use mesh with your Fourier modes. You have to have enough degree of freedom, enough basis. Otherwise, something happens here. Then what is the good things about, I said a lot of things about the bad things about the global basis, but what good things about global basis? Because especially sign. Okay, let me say the global basis we talked about is ReLU. Well, only this point is useful. This piece is not useful. So it's very localized in space. Only this singularity here detects something about function. You use arc tangent, only this region is of interest. This is like a constant, this is like constant. Sign, everywhere is useful. So, okay, so why are you, so you, later on, basically, my already give you things. If you use activation function, use especially our later, using our later neural network structure, use this if possible as activation function. And why using global function? Because if you have a smooth function is global. So which means if you have something like this, you only give a point here, a point here, a point here, here, good enough to describe this, okay? And your global function will fill every point. So you can use sparse sampling and global activation function like sign. You can easily approximate smooth function, even in high dimension. Smooth function is easy for two-layer using global activation function. Okay, then you see, okay, is that curse of dimension? Of course not, because smooth function in Fourier domain is localized near origin. You're not can conquer curse of dimension. You just say, I'm going to be able to detect something global, smooth in space, but local in Fourier domain. Okay, so it's not. So, but remember this, you can use linear combination of a random of sign things to approximate very effectively smooth function, because even learning is quick because you only use the leading modes. You approximate of smooth function, you only need to use leading modes. Okay, that's very important. So training A with a diverse set of activation function with random WB is good enough to approximate smooth function. And gradient descent method is very friendly to gradient descent based method because you only need to use the leading mode. Proper scaling of the initial can improve the things. Okay, so quickly I use 5 or 6 minutes to finish by from shallow to deep. The shallow to deep is saying the composition. Well, if you know, a multi-layer neural network is nothing but a combination of single-layer networks. And the key things I think here is try to use composition and combination of smooth function to approximate non-smooth function. The things we didn't explore before is composition. Okay, all the previous things, what I mentioned in linear representation, we all do very well, know very well. But composition is even composition of smooth function. Combination, I can easily give you examples to do that. They can come, you just stretch by 2 times. The first layer just approximate 2x, and next layer instead of sine 100x, you reduce to approximate sine 50x. Okay, so that's already reduce the frequency very quickly by layers, exponentially quickly. Each smooth function can be approximated by linear combination of random bases, which is neurons here, okay? And can be trained effectively by gradient descent-based method. Also, I would emphasize, I don't, just like when we learn linear algebra, the most boring, difficult way to understand the matrix is think of matrix of n-squared numbers, every number you care about. It's the column, each column, and the linear combination of the columns that make the difference. It's not every element. So you shouldn't emphasize about each neuron, each parameter, but rather here, we really want to understand a linear combination, use a linear combination as each neuron as basis to do some easy task, approximate a smooth function. Okay, structure. Good balance, also fully connected. Where is the problem? Even from 1D, if you have a 10,000 network width, you immediately raise yourself to 10,000 dimension, and you live in 10,000 dimension, never come down until the last step. Here we have something in the between is really this 10,000 is a basis. Maybe I only use 10 different linear combination of this. It's good enough to grasp the information. Okay, of course, the ultimate adaptation is what? You only need one dimension space approximate function because your function is just one function, right? But here I give you something, but it's not going to 10,000 dimensions. So we have this. So if we call it multi-layer, okay, so optimization, you have to is usually the bottleneck. Mathematical, okay. So here I say mathematical approximate theory without effective optimization is really of little in practice. You see, there are so many approximations, nice result, None of them can make a difference in real practice. You need computation to do that. The goal is the highly adaptive nonlinear approximation through efficient learning using linear representation. Okay, so I give you the references. Please take a look. It's very simple modification of the fully connected, but it can reduce significantly the total degree of freedom, so on and so forth. It's very easy. I don't want to do that. Okay, I just give you an example. 2-layer can reduce learning of cosine 100x to learning cosine 50x. Okay, so here the summarize about our most recommended. Please, if you want to do this, and just very simple to try. I give you the link to the GitHub link. Using sign activate function, using our network, and then scaling of a parameter initialization. And we have good approximation theory, very beautiful. But again, as I said, this just showed fully potential. It really doesn't tell you too much what is going on in real practice. Again, I'm proud of showing this, but I'm always sorry to tell you, this theorem, beautiful as it is, really doesn't imply too much in practice what is going on. Okay, so now we're trying to even to show how much our network can do. 1D, like this, it's at least more frequent than this, and has a discontinuities, not discontinuity, non-smoothness is not only C0, not even C1. Okay, there's taking the integers and so on and so forth. You see, we can really goes to 3-digit. This is more than 3-digit. Okay, this is the mean square error. So you take a square root, it's 3 to 4 digit for this. 2D like this, we can also reach 3-digit. And we're trying to cook up a function. Now we think we have another one which has a okay, I'll talk a little bit later. So this one, it has oscillation outside, has this non-smoothness. Does not fit Fourier series well does not fit finite element well unless you do adaptive finite element. But that's a nonlinear process. In 2D, 3D, 4D, 3D, 4D, you cannot even want to do that. It's very complicated. 3D, 4D, you even don't know how to do it. But for this, so we want to compare with the traditional method, FFT, with the same number of degree freedom. This is FT. This is finite element. This is ours. Okay. This is not ours, which is ours. Fully connected. This is ours. Okay. At least maybe a little better, but it's comparable in terms of degree freedom. This is the best method, traditional method you would use. And here it's showing if you're using Fourier series to approximate sine 100x from -1 to 1, it's periodic. So it's very easy if you include 100 in there, frequency 100 in there. But you approximate this one wouldn't be that easy. It's not periodic, although it's almost 100 frequency. In terms of oscillation, it's about the same. But for our method, you don't see the difference. Okay, this is even better sometimes. Okay, I'm concluding right now. It's just, there is no mystery. It's a way of parameterized nonlinear representation. It's a strength, it has weakness. You should know that in order to know well, in order to use it, not just use it as a black box. To understand meaningful computation is crucial. Composition is powerful. That's what I want to say, but subtle. One thing is interesting. The coefficients you finalize, you compute it here, is highly non-unique because composition is unique, right? Sine 100x, you can think of sine 2x composed with 50x or 25x composed with sine 4x. There's non-uniqueness. So that's a little bit problem. So for example, even have a very good approximation, the parameters doesn't tell you much about the function because it's not like sine series or linear representation. If your basis is linear independent, the representation is unique. Here is highly, which you need it for your flexibility to do adaptivity. You want something, you have to sacrifice something. Training usually is the bottleneck. So please, some people say, okay, I assume I can find the optimal, then I prove the things. I think that's a big if. That's a big if because using gradient descent is highly, highly difficult to find the global, even local minimum if it's ill conditioned. Which most likely is. You have over-parameterization, billions of parameters. So adaptivity, gradient descent, okay, stability. Okay, so difficult level, so which means you need to use a larger and larger network when it's more difficult. Global high oscillations, that's difficult. Well, the most difficult, local fast transition, less difficult. Smooth function is easy. And usually if you use red loop, you definitely know you will have some stability, but usually you will have some problem in accuracy. But using sine, all the things, if you do not well, it can still overfitting. It's no surprise. More accurate you have, you're more sensitive to high frequencies. Less sensitive to high frequencies, you're more stable. You cannot gain both. There's no way you can gain both, okay? Life is always a compromise. And a friendly setup neural network is, say, in our traditional method for sine, for this oscillation, usually we put 10 points per wavelength. Usually that's marginal good resolution. But when you use neural network, you'd better use more than that because otherwise you can either not accurate or can cause overfitting. Okay, so that's the end of the thing.
Okay, thank you very much for this insightful talk. Are there any questions from the audience? Okay, so first one, I know that I'm going to use structure is very important. Very important. And the extent of the classical value of these functions at the value of the smoothness.
Yeah, I think, as I said, if I'm approximating a function, it's a real physical function where the Fourier frequency, right? If in some arbitrary embedding, the frequency mode doesn't mean much, right? The scaling. For this particular scientific computing, I think the frequency mode, the frequency domain seems to me has a better way to describe things than using physical way because your active function or global. Global in space, which means you're more local in Fourier domain. So you can describe it better. Yes, because you're using global activity function. Barren stuff, I think, is just a way to tell you, okay, I'm giving you a space that is so small, you can do a good job. But also in there, again, even all this has universal approximation theory. I show you the sign things, you can approximate a continuous function very well, but the difficulty is the optimization. Existence is far from you can find it. All those things, it just says there is a representation that can find that, but how do you find it? That's a big issue. But also no gradient design that doesn't still it's not you cannot provably showing that it's gold. Greedy algorithm is always something you want to do in practice, but greedy algorithm doesn't usually you cannot show it's really convergent to globals optimal because those constructions are highly constructive. It's not where the computer doing this. Maybe this greedy one is a little bit better, but I think, if you, first of all this function I'm talking about, the Barron space norm is huge. The Heron space is huge. It's huge. Because for them, it's the total sum. Total sum is very small. That means dimension doesn't play a role, right? If I'm talking about 100 frequency mode in 10 dimension, the whole Fourier ball is so huge already. It will also be huge. If you have this oscillation here, it will be huge. It'll be huge. Yeah, it will be huge. So there's always something embedding in there. There's definitely some dependence on the dimension. Yeah, 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 yeah. I think the best thing is, in 2D, 3D, we have a lot of interesting functions. In our website, you have different kinds of functions. Try to approximate those functions. You will see how difficult it is. Yeah, very good. You know the detail. It looks like so, but remember the very important structure of and if you look at it, look like that. But in our two matrices, this is W. This one is randomly given. You don't change it. You don't change. You only optimize this A. That's the A corresponding to the A I am saying. In before, they just write into two low rank. Each of them, you have to train them. Here, this is randomly given. And you compose them. And it's also not random feature method because this is changing and you compose. It's not fixed anymore. So only half of them is training. Yeah. Yeah.